Now let's look at the big omega notation. So just as the big O notation provides asymptotic upper bound, the big omega notation here provides a lower bound on the function. So we use the same language to define the big omega notation. It'll be like, it's also the big omega of g of n is also a set of functions. And for any function in this set, it must satisfy that we can find a constant c and n0 such that the target function is greater than c times g of n for all the n that's greater than n0. Okay, so now we put the g of n to be a lower bound here, right? So intuitively, we can think of the we can use this chart to think of the relationship between fn and the c times g of n. So for anything that's above n0, the f of n, the function fn is always greater than the c times g of n. Okay, so the big omega notation means that no matter what particular input size n is chosen, the running time on the input is at least a constant times g of n. So it's kind of a reminder that we need to consider the best case of the inputs. Okay, so that's big omega of the big omega notation. So now we have learned about the three notations, and there's actually a very close relationship between these three notations. So for any, there's a theorem that here we will talk about. For any two functions, fn and g of n, we will say that fn equals big theta of notation, big theta of g of n, if and only if, first, the g of n is an upper bound of fn described by the big O notation, and g of n is also a lower bound of fn, right? So this is a very straightforward theorem, because by the definition of big theta notation, it requires both the upper bound and the lower bound. Okay, and usually we use this theorem to prove the whether a function is a tight bound or not. Okay, so we need to first prove that it is an upper bound, and then prove again that it is a lower bound. Okay, so in the next video, we're going to revisit the insertion sort algorithm, use the big theta big O and the asymptotic notations.